Hello and a warm welcome. We will now present to you a solution to deal with the problem of biogenic corrosion in sewer networks and wastewater treatment plants using the calcium aluminate mortar Sika Monotop 4400 MIC. MIC standing for Microbial Induced Corrosion. This presentation has been prepared by Mr. Michel Donardio of Corporate Target Market Refurbishment. In this slide, there are 4 examples of concrete damage caused by biogenic corrosion from around the world. This type of damage can occur quickly, as shown in the photo in the bottom right. The concrete has decayed underneath a bridge in a primary sedimentation tank. This photo was taken in a plant near Mexico City less than 5 years after commissioning. Concrete damages occur in the aerial part of the structure above the waterline, as shown in the 2 pictures. Concrete beneath the water flow shows no sign of concrete degradation. But how does biogenic corrosion occur? The pH of the water is close to neutral. Wastewater in sewer is charged with organic matter and contains sulfate and bacteria. Bacteria in the sewer, in the absence of oxygen, transform sulfate into hydrogen sulfide, known as H2S. H2S is released in the aerial part of the sewer during turbulences and long transportation. Due to other bacteria in the aerial part and in the presence of oxygen, this hydrogen sulfide is transformed into sulfuric acid, H2SO4. This acid attacks severely concrete and mineral substrates. The following video was taken during inspection in a main collector sewer in Paris. The owner of the structure commented, "The problem was not so serious in this specific location as the surface of the zone repaired some years before was looking homogeneous." Obviously, the owner's comment was an understatement. We can clearly see in this video the soft material easily being scraped off is gypsum that has been produced by the acid attack. Soon the reinforcement bars will start to corrode, placing the structure in real danger. The next video was taken in a concrete pit of a small pumping station near Casablanca in Morocco. The pH measured at this location was around 1, as shown in the embedded picture. Note how easy the damaged concrete can be removed. But why are these aluminate mortars, and particular Sika Monotop 4400 MIC, are efficient to mitigate biogenic corrosion? In a nutshell, it prevents the transformation of hydrogen sulfide H2S into sulfuric acid H2SO4. However, there is more than this to this statement. The next few slides will explain in more detail how these aluminate mortars are efficient to mitigate biogenic corrosion. The first barrier is a higher neutralization capacity of acid compared to ordinary Portland cement. In simple terms, aluminate mortar will resist longer than OPC in contact with acid. But this does not explain on its own the superior durability of these calcium aluminate mortars. The second barrier is due to the nature of the calcium aluminate mortar, where, when the pH goes lower than 10, there is a precipitation of aluminum hydroxide gel, AH3. This gel is very stable down to a pH as low as 4, and it acts as a barrier against further attack. At this level, the mortar is not much affected. However, during this time, bacteria continues to transform H2S into acid. So, as bacteria continues to generate acid, the pH will fall below 4. At this stage, alumina ions are released. But before to go into more details in this most important barrier, let's explore what is happening when resin coatings or Portland cement-based mortars are used. In the case of resin coatings, or an inert liner such as HDPE, there is no buffering of the pH. As soon as there is hydrogen sulfide in the aerial part and the presence of bacteria and humidity, This H2S is transformed into acid and the pH drops immediately to a very low level, as shown in the animated graph. If the coating or liner is free of defects, has cured properly in terms of temperature and relative humidity, and if it is adapted to this environment, it can resist for some time to this aggressive condition. However, if there are localized defects, inappropriate curing conditions, or variations of the thickness, the acid can propagate beneath the inert coating or liner, attacking the concrete underneath, leading to severe deterioration of the substrate and the liner. This slide shows some examples, amongst many, of damages despite previous protection. The photos on the left show severe damages of concrete in Singapore. The concrete was previously protected by a HD PE liner. The photos on the right, taken in a small confined chamber in France, show damages of the concrete happening a few years after application of a protective coating. The in-depth investigation that followed this claim concluded that the damages were due to an inappropriate application. Now let's have a look at the behaviour of concrete or Portland-based repair mortars. Initially, due to carbonation, the pH drops, and when certain conditions arise, acid is formed due to the biogenic activities, and the pH drops continuously to around 2, in some cases even 1, like in the photo from the project in Morocco. Now let's go back to the behaviour of the calcium aluminate mortar with the third barrier, called the bacteriostatic effect, and the most effective. Initially, the pH drops due to the carbonation action, and a bit of acid is generated to the biogenic activities. As mentioned in the earlier slides, as soon as the pH drops below 4, alumina ions are released and inhibit the activities of the bacteria, preventing further the transformation of H2S into acid. The pH gets stabilised around 3 to 4 at a level where calcium aluminate mortars are not so affected. These lines on the graph are plotted from artificial weathering tests results made in several incubation chambers. The first two lines, in grey and orange, are from a report commissioned by Sika, and the black line from a report commissioned by a friend in the market. But it can be applied to all types of reactive resin or HDPE liners. These curves match the theory described in the previous slides. With inert liners or coatings, the pH drops immediately to a very low level. With concrete or cement-based mortars, the pH drops to around about 2, and in some cases even below 2. With 100% aluminate mortar, the pH gets stabilised between 3 and 4. These curves are extracted from the previously mentioned Sika commissioned report, made by the Fraunhofer Institute in Germany. The curve with good quality concrete using slag and silica fume shows heavy deterioration. The curve with alumina cement, but the sand being silica, resists better but nevertheless is severely attacked. The reason being is that approximately 75% of the mortar surface, due to the presence of silica sand, does not stop the proliferation of sulfuric acid. The last curve, 100% calcium aluminate mortar, shows when the whole matrix, cement and aggregates, is made of calcium aluminate. The degradation is actually very low. These pictures show the aspect of the different specimens after 1 year in the incubation chamber. This is equivalent to approximately 8 to 10 years in a real-life sewer. The picture on the left shows very little degradation of the aluminate mortar. Actually, the compressive strength carried out on these calcium aluminate specimens shows similar values to the reference concrete stored in normal conditions. The other two pictures show much heavier deterioration. Beware of the statement, which reads, "Product X is a factory blended, one component, fibre reinforced, 100% calcium aluminate cement designed to provide excellent corrosion resistance against typical hydrogen sulfide gas, microbiologically induced corrosion." The picture in the middle above shows the aspect of these products after 1 year in this incubation chamber. What about the real-life environment? Let's have a look at this study done by a well-known research laboratory, IFSTAR, in France. Proteccion is situated in the southwest part of France and generally experiences mild winters. The area is one of the favourite zones visited by the people from the Paris regions, meaning in the summer the number of inhabitants rises significantly, from approximately 137,000 up to 400,000 during the peak season. The sewer network and the wastewater treatment plant was designed to cater for this influx of people during the summer. This means, during the mild winter and intermediate seasons, the network is nowhere near capacity, with a low water level and a high aerial part prone to biogenic corrosion. The picture on the top right shows clearly the damages of the biogenic corrosion in this confined chamber. Different specimens made of Portland cement, CEM 1 and CEM 3, supposedly resistant to chemical environment, and a specimen of 100% calcium aluminate mortar are placed in the aerial zone prior to putting back the cover on top of the chamber. The study lasted more than 6 years until the complete destruction of the specimens made with Portland cement, CEM 1 or even CEM 3 type of cement recommended in wastewater environments. Both videos show clearly the difference between the Portland cement specimens and the one made with 100% calcium aluminate. The soft material that is easily removed is gypsum. Remember the video taken in a large collector, presented earlier, regarding the inspection with the owner. The soft material which was removed was also gypsum. Only the CEM 1 cement is shown in this video. However, there was no significant difference with the CEM 3 specimens. The calcium aluminate mortar specimen is practically not damaged at all. Only slight surface pollution is noted. The graph in this slide shows the difference in behaviour between 3 specimens and the degradation rate per year. Data in this field experiment shows that a 100% calcium aluminate specimen has a deterioration rate of only 100 microns per year. This is backed up by field results where, 23 years after application, the mortar surface is still sound and the pH was measured at around 3 to 4. The very low degradation rate of the aluminate mortar confirms the visual aspect of the specimens after this period. With 100% aluminate mortar, all the concern of using resin or inert liner system, which led to numerous claims and court cases, is removed. Efficiency in presence of sulfuric acid is no more an issue, as after some time the acid is no longer produced. Humidity. This is needed for this mortar. Surface requirement. Mortar needs to be applied on rough surface and does not require a specific smooth finish. VOC. This is a water-based system. Time constraint. Typically 12 hours after application, handover can be done. Durability. Proven by test experiments as well as from investigation on old projects up to 23 years old. This slide shows just a few of the references from different parts of the world using 100% calcium aluminate technology. There are different weathering conditions and site situations. Compilation of these references is available upon request. The last 2 references on this list were completed with Sika Monotop 4400 MIC. Now let's have a look in the next few slides at the different steps for application, starting from the surface preparation. First, the damaged concrete needs to be removed. One of the best ways to remove damaged concrete is the use of hydrojetting. Other methods, like grit blasting, are also used. This slide shows the different steps prior to applying the mortar. Sound concrete must be reached and all corroded parts removed. Remove contaminated concrete until a minimum pH 10 is reached. Roughen the surface to provide enough mechanical key for good bonding. The surface shall be saturated dry prior to placing the mortar, wetting for at least 2 to 4 hours prior to starting work, or better overnight wetting. The picture on the bottom shows part of the surface sufficiently pre-wetted, and a part not wetted sufficiently. Now let's have a look at the different application techniques. The mortar can be applied using a low pressure wet spray, a hopper gun for small surfaces, the dry spray method, a spinning head, e.g. slinger unit. Manual application is not recommended for large surfaces. From left to right, there are some examples of projects using Sika Monotop 4400 MIC. The first picture was taken in a project in France where more than 100 tons of mortar was applied using the dry spray process with very low wastage, approximately 12%, and low dust emission. The second picture was taken in a project in Belgium where the product was applied through a spinning head on a masonry manhole. The third picture was taken in manholes renovated in the Netherlands. We can barely see the operator applying the mortar using the wet spray technique. And finally, the fourth picture was taken in a project in France, and for a small area, the applicator has used a hopper gun to place the mortar. The thickness of the application is not related to the durability, but to the behaviour of the material towards drying and shrinkage. This is based on more than 25 years of experience from site application. In general, it is recommended to apply approximately 25 mm. Only for small diameter manholes of less than 1.5 meters or small surface areas, the thickness can be reduced to approximately 15 mm. The video shows typical finishing works. It is not needed to have a perfect smooth finish. A final touch with bloom is good enough. The curing shall be done as soon as the surface is hard enough. Use only wet curing. Classic curing compounds do not work with calcium aluminate cement mortar. If a quick return to service or quick curing is required, use Sika Guard 230 MIC surface hardener. The photo shows the application of the surface hardener using a low spray pressure gun, a garden type spray equipment. This slide shows an example of pre-wetting and wet curing in a channel of wastewater treatment plant in Strasbourg, France. This is another way of pre-wetting and curing the concrete surface in a very small congested confined pit in a wastewater treatment plant in Angers, France. Let's summarise what has been shown in this video. Sika Monotop 4400 MIC is produced by Sika. It is based on 100% calcium aluminate technology. The aggregates used in the mortar are crushed from the same clinker produced for the cements. Both cement and aggregates participate to the inhibition of the transformation of the hydrogen sulfide into sulfuric acid. Sika Monotop 4400 MIC is produced in a CE approved factory and complies to EN 1504 Part 3 as a Class R4 repair mortar and to EN 1504 Part 2 as a protective coating. The factory is certified to ISO 9001, ISO 14001 standards for quality of the product and control of the environment. Sika Monotop 4400 MIC combines repair and protection in one single operation. It can also be used for a structural repair, Class R4 mortar according to EN 1504 Part 3 European Standard for Repair Works. This was the case in a renovation work in Singapore where a chamber was refurbished with a 40mm calcium aluminate mortar using the dry spray method. No bonding bridge or additional protective coating is required. In one single step, the structure is repaired and protected against biogenic corrosion. Sika Monotop 4400 MIC can be applied using a dry spray or wet spray process. It can also be placed on the surface using a spinning head spray. Typically, handover can be done within 12 hours after application. If a specific surface hardener is used, such as SikaGuard 230 MIC, the handover timing can be significantly shortened, and a soft opening can be done 1 hour after application. The surface hardener is also used when there is a need for early wet curing during renovation, for example in the presence of a strong ventilation for worker safety. And what about efficiency and durability? This slide is the main message. The efficiency is because the calcium aluminate mortar inhibits the transformation of hydrogen sulfide H2S into sulfuric acid, and therefore the sewer is no longer being attacked by the acid, hence its very long durability. Sika is your right partner in the refurbishment of wastewater treatment plants and sewer networks. Whether in renovation or a new project, Sika has a wide range of different technologies and product solutions. Here are just a few more examples of Sika solutions working in sewer networks and wastewater treatment plants. For repair works, one component repair mortars, abrasion resistant mortars, high performance resurfacing mortars, various systems for joint compounds for aggressive environments, steel protective coatings, specific systems for mechanical scrapers, protective coatings for chemical aggression, protective coating for biogenic corrosion in digesters and biogas tanks. For more information, consult www.sika.com or by using the QR code. This is the end of the training module, and we hope you learned something new. Please do not hesitate to contact the relevant technical department of your local Sika organisation. We thank you for your attention.